Good morning, class. We are looking at section 3.9, related rates. So there are a lot of formulas of differentiation we're supposed to know. Hopefully we are comfortable with that. And now we are going to move on to the next section. And the last section we covered was exponential growth and decay. So a couple of things. dy dt is equal to, let me just put this in, when dy dt is ky, okay, when the rate of growth is proportional to the actual function, dy dt equals ky, okay, then it becomes an exponential function, y equals ce to the power of k. And it was extensively discussed. Basically, when k is positive is exponential growth, negative is exponential decay. Newton's law of cooling was discussed, where capital T represents the temperature, lowercase t is the time, y sub 0 is the difference between the initial temperature and T sub s, which is the surrounding temperature. And then the related rates is discussed, that it's coming up right here. So let's go to related rates. If you're pumping air into a balloon, the volume and the radius of a balloon are increasing. But what happens is that measurement for one may be easier than the other. So in a related rate, what do? We find quantities, we relate them using some sort of equation, normally from geometry or maybe trigonometry. We put them together, and the procedure is, after finding the equation and relating the two quantities, we differentiate, and the differentiation is normally using the chain rule. So we're going to use the same example, but now with numbers. So dy dt equals dy du dt. So what do we mean by this? So we get the very first example. Air is being pumped into a spherical balloon so that its volume increases at the rate of 100 cubic centimeters per second. We want to know how fast the radius is increasing when the diameter is 50 centimeters. So the very first thing is we are looking at a spherical shape, okay? And we want the volume to be related to the radius, which means we have to find a relationship between the two. And I hope you remember the volume of a sphere. Anybody remembers the formula for the volume of a sphere, class? So the rate of increase of the volume is given, the rate of the increase of the radius when it is 50 centimeters. So the volume of a sphere is 4/3 pi r cubed. Now, anytime we do word problem, it's important to understand the problem by reading and rereading, see what's given. So I wrote the given, and more importantly, we have to do it symbolically, class. So we need to see how this works symbolically, okay? So to do that, we are going to write the rate of increase of the volume as what? Remember, the volume is 4/3 pi r cubed. So dV dt is given, okay? dV dt is given as 100 cubic centimeters. We are interested in finding dr dt at a specific moment when r is 50/2, okay? In other words, you recall that d equals 2r. So having said that, let's move on with this by simply the process of differentiation. Now, remember, the volume is 4/3 pi r cubed, okay? So you want to differentiate this. And to differentiate this, you realize that dV dt is of interest to us, where v is a function of r. So therefore, you're using the chain rule. dv dt is dv dr times dr dt. I hope you see that, everybody. Now, let's see what's dv dr. First of all, 4/3 pi is just a number keeping. Then r cubed gives you 3r squared, and then dr dt. So this portion without the dr dt is the first portion, dv dr. So if you take the derivative of the volume with respect to r, you get 4/3 pi times 3r squared. Done. But since we want it with respect to time, we are going to add dr dt, okay? We are going to add dr dt. So I hope everybody's following that. Now, of course, we simplify this, 4 pi r squared dr dt. Practically, we are done. The rest is basic algebra. Understand the left side is dv dt, which is given, 100. And the right side, pi is not missing, r is given as 50/2 or 25. Find dr dt. You have a choice, plug in, calculate, plug in and calculate. Or instead of doing that, you can solve for dr dt. How? How do you solve for dr dt? We divide by 4 pi r squared, both sides. Division by 4 pi r squared is the same as saying times 1/4 pi r squared. So one more time, division by 4 pi r squared, both sides goes away, and the left side is 1/4 pi r squared. I hope you realize this is just division, right? Multiplication by the reciprocal, that means division by the expression itself. Now plug in. So the RDT is dv dt, which is 100, 1/4 pi r squared, 1/4 pi 25 quantity squared. By the way, don't forget that whatever we do to units, we do to whatever we do to numbers, we do to units. So this 100 is 100 cubic centimeters per second, okay? And this one is 25 centimeters squared, so this is centimeters squared. If you were to write the units for this one is cubic centimeters per second, and for this one is 25, and it's being squared, 25 squared, okay? Now you can simplify this and you get 1/25 pi, because 100 is the same as 4 times 25. You can simplify it. I hope you see the simplification. In other words, you can say 100 will drop 4 times 25. You get 1/25, and cubic centimeters per second over centimeters squared gives you the units of centimeters per second. This is the precise answer in calculus. That's good enough. If you replace the pi with 3.14159, that's what you get. And don't forget the proper units. Again, I took, I think, a fairly long time on this question because we wanted to get this started. All right, so let's move on. Could somebody read this example? I need you to help me so we can go through this fast. Could somebody be kind enough to read the question, please?
I'll read it.
Please.
A small rock is dropped into a lake. Circular ripples spread over the surface, with the radius of each circle increasing at a rate of 3/2 feet per second. Find the rate at which the area of a circle is changing when the radius is 4 feet.
Thank you so much, Joseph. So what do we need to understand? Quickly as we read, we see the radius and circle. Okay. All right. So the radius is increasing at the rate of 3/2 feet per second. We want to find the rate at which the area is changing. The area is changing. That means we need to relate the two. And so the very first thing is some basic information from geometry. A equals pi r squared for a circle. D equals 2r. C equals 2 pi r. And of course, we need the area. Okay, class? So what is given? Okay, what is given? dr dt. What is missing? dA dt. When do you need that? When r is 4 feet. So take a look at symbolic way of translation of this question. Symbolic. A is pi r squared, everybody. Dr dt is 3/2 feet per second. Okay. R is 4 feet, and we are looking for the dt. This is a very simple case the moment we get here. Okay. So we want the ADT. So take a look. The ADT, you take the derivative with respect to r, becomes pi times 2r, which is 2 pi r, and then tag along the r dt. So pi times 2r times dr dt, or 2 pi r dr dt. Everything is there. Look at the given. That's why this line becomes extremely important for your reader, including yourself, sometime down the road, to remember what she did. Pretty much you have everything you need here. Just plug in. Okay. So 2 pi, and then r is 4, and by 4 we mean 4 feet. 4 feet. And then 3/2, the RDT is 3/2 feet per second. That's why it becomes square feet per second. In other words, I hope you pay attention to the units, and I hope you realize this is an approximation. You multiply, you replace the pi with 3.14159. What I want you to pay attention to is the ADT. So what are the units? The units of area over the units of time. So that's why square feet over second. So I'm going to emphasize on that because I want to make sure you're comfortable, okay, with finding the final units. dA, dt, change in A over change in time in essence. But this is a instantaneous rate of change. So could somebody be kind enough to read this question, please?
I can read it, Professor.
Thank you so much.
Example 3. Falling sand is forming a cone-shaped pile. The volume of the cone is increasing at a rate of 45 pi inch cubed per minute. The height of the cone is twice the radius of the base. Find the rate at which the radius changes when the radius is 6 inches.
Fantastic. First and foremost, cone. I hope everybody remembers the shape of a cone. Okay. Then the volume of a cone. So we need the formula for the volume. Okay. Anybody remembers the formula for the volume of a cone? Volume equals 1/3 pi r squared h. So the volume is increasing at a rate. So this is what? dV dt. The height, h, is twice the radius, is 2r. Find the rate at which the radius changing. That means the r dt at the moment that r is 6 inches. So we want to translate this. I can't really emphasize this enough. First, the formula, piece of information from geometry. Then the very first piece is dV dt, and don't forget that it has a units, cubic inches per minute. In other words, the units of the volume per unit of time. Over here says the height, h, is twice the radius, h is 2r. And then we want to find which rate, the rate at which the radius changes, that means the r dt, at a precise moment when r is 6. Now, one of the things I want you to notice is the following. If you just look at the volume, itself has two independent variable, r and h. It depends on the radius and h. I want you to know that. By any chance, if anybody wants to differentiate that, it uses the product rule in conjunction with the chain rule, okay? So what do? H is 2r. Because we want the r dt, we are going to get rid of the h. If we wanted the h dt, we would get rid of the r. So h is 2r. The very first thing, replace it here. So that's the first thing we do. Replace the r, replace the h with 2r. And then we get 2/3 pi r cubed. Now we go with dV dt. which is given as 54 pi. So find dv dt. What is that? 2/3 pi. That's a number. That's a coefficient times. Now r cubed with the 3r squared, and then it's dr dt. So dv dt is 2/3 pi, and then 3r squared dr dt. Simplify by dropping number 3, and this is your final answer for dv dt. 2 pi r squared dr dt. And we know dv dt is what? 54 pi cubic inches. So all you have to do divide both sides by 72 pi, and that's your answer. 3/4 inches per minute, the units of the radius per unit of time. Okay, and the reason is very simple, class. Remember, if you go back to this dVdt has cubic inches per minute as a unit, and the right sides, because I want to make sure everybody understands what's happening. The left side here, okay, cubic inches per minute. The right side has r squared, so we have inch squared. When you divide, you're really dividing by inch squared. Okay, that's how you arrive at the answer. Okay. We want to look at this question. Could somebody read this one for us, please?
A 20-foot ladder leans against a building. The base of the ladder slips away at a rate of 2 feet per minute. Find the rate of change of the height of the ladder when the base is 12 feet from the building.
Thank you so much, Ethan. So what's going on? Well, we have a ladder that is leaning against the building. And then it's going to go this way. And the tip of the ladder is going to come down. So it's going to move this way. That creates dx dt in this direction. If you call this x, you can call it anything you want. Resulting in this shape, and this is coming down, creating dy dt. Okay, so we are going this way, and the ladder is coming down. So when we go this way, it gives rise, okay, to what? A couple of things. First of all, when we say a 20-foot ladder, that means this hypotenuse, if you look at this shape, is a right triangle. This hypotenuse is fixed as at number 20. The base is moving at 2 feet per minute, so dx dt is 2 feet per minute. We want a rate of change of the height. The height, we used y, so we want to know what's dy dt when we know x is precisely what? 12 feet. So this uses Pythagorean theorem, x squared plus y squared equals 20 squared. So, in other words, we are using a squared plus b squared equals c squared. Okay, class? Okay. Now, this is pretty straightforward. All you have to do, differentiate everything with respect to time. We are looking at this one, and remember, we use the Pythagorean theorem. So x squared gives you 2x dx dt plus y squared gives you 2y dy dt, and this is a number. It doesn't matter, it's 400 or any other number. Needless to say, everybody knows this is 400. And it's 0. Okay, now let's see what we have and what's missing. Okay, we have x is 12. We have dx dt is 2 feet per minute. Then y we don't have, dy dt we don't have. But when x is 12, we can use Pythagorean theorem to find y. So replace the x with 12 now to find the y. I'm assuming this is an easy calculation. Okay, elementary algebra. Y becomes 16 feet. Now we have everything. So we're going to replace x with 12, dx dt with 2. 2 is there. Y is with, we replace it with 16. We find dy dt. Again, it's an extremely simple elementary algebra calculation. Solve for dy dt, and you get negative 3/2 feet per minute. Please bear in mind, all the units do work accordingly. What I want to add here, and this is extremely important, is to pay attention to what happens to x class. X is increasing. Dx dt is positive. What about y? It's decreasing, and dy dt must become negative, and it does. Okay. Now, we're going to look at exactly the same question. We're going to repeat everything. Now, notice not only y is changing. If you look at this angle class, which we're going to call theta, this angle is also changing. So we are looking at the same situation. Okay. We are looking at the same situation, everybody. But this time we want to find the rate of change of the angle between the ladder and the ground when the base is 12 feet. Now, I'm going to repeat what we had in the previous page, but for finding that there is a need for a different equation. And I wrote that because I'm just repeating the previous page. Okay, class, I'm just repeating the previous page. And this one comes to work, but not for finding d theta dt. Okay, so to find the d theta dt, you have to find the relationship between theta and the given. What is given? Okay, x. Now, can you find the relationship between theta and y? Yes. The reason I rather deal with x because x is given. And when we go with y, maybe we made a mistake with our calculation. We don't want to take a chance. Okay, so that's important to see why we stick with the given. So if you look at the relationship between the two, okay, first of all, understand that sine theta is y over the fixed hypotenuse, y over 20. Cosine theta is the adjacent x over the hypotenuse, which is 20. And we're going to use this one specifically because x is given. Okay, if you trust your calculation, you can use y. We have already calculated y from the previous page. We're going to use that, but stick with the given. Therefore, you're going to write cosine theta is x over 20. Now, this is a very simple differentiation. Okay, before we do that, I want everybody to see this is the same as saying 1 over 20 times x. And I say that for the sake of differentiation. So you're differentiating both sides with respect to t. So cosine gives you negative sine. So negative sine theta, and then d theta dt. And this gives you 1 over 20. X gives you dx dt. So take a look at what happens. Minus sine theta, d theta dt, 1 over 20, dx dt. Okay, so when we look at this, we see we have everything except sine theta because we have dx dt, right? So what is sine theta? I have mentioned sine theta is y over the hypotenuse. We have already calculated y to be 16 from the previous page. Okay, so we plug in. So minus sine theta. Sine theta is y over 20 class. Okay, so sine theta is y over 20. Okay, so minus 16 over 20. Now you can drop the 20. Okay, you can drop the 20 because they are both denominators, and you can simplify the rest. So minus 16 d theta is 2. So d theta dt, I mean, d theta dt is 2 over negative 16. 2 over negative 16 simplifies into negative 1 over 8. Now, what I want to mention would be the units. The units for angles in calculus is always radians unless otherwise mentioned. Therefore, is negative 1 over 8 radians per minute. Radians per minute. I can't emphasize this enough. Okay, class? Radians per minute. Okay. Could somebody be kind enough to read this question for us, please? Anyone?
I could.
Sure.
Two cars leave an intersection at the same time. One car travels north at 35 miles per hour. The other car travels east at 60 miles per hour. How fast is the distance between them changing after 2 hours?
All right, so we are right here and we are moving as it was described here, okay? So one goes up north and one goes towards east. So we are going to write the given according to this. We want to know how fast their distance, here's their distance, okay? That is changing sometime later, in this case, 2 hours. So what is given? Okay, so we are interested in that. So this is the distance z. Those are x and y, okay? So what is given? Dx dt is 60 miles per hour. Dy dt is 35 miles per hour. Dz dt is missing at t equals 2 hours, okay? So the formula, obviously, it's Pythagorean theorem, a squared plus b squared equals c squared, or simply put, x squared plus y squared equals z squared. I hope everybody knows that. But before even we go there, the value of x, I hope you see the x dt is 60. So 2 hours later, x is 2 times 60. And 2 hours later, y is 2 times 35, okay? So we have those values, okay? Comes from d equals rt, okay? So we have those values 2 hours later. This is a simple calculation. So perhaps we start with x squared plus y squared equals z squared. A very simple differentiation with respect to t gives us 2x dx dt plus 2y dy dt equals 2z dz dt. Now you can even drop the 2 from both sides. In other words, you're factoring 2. You can do that, or you can do it at the end. Or just plug in. The reason I calculated those because we need it here. So we replace the x, we replace the dx dt, we replace the y, we replace the dy dt. Now the right side, what about z? Z, you have to plug in x and y to find the z. Okay, class? Okay, and that means 120 squared plus 7d squared is z squared, and finding z this way. I hope you realize what we did, okay? You add up those two numbers, you take a root. Precise answer is 10 square root of 193. Just do the math and find dz dt. This is now a simple calculation, okay, from Pythagorean theorem. And that's your final answer. So I hope you see how we arrive at the answer, class. It's pretty simple. Just plug in whatever you have. The missing z comes from the Pythagorean theorem again, and you can finish the job. All right. This is the same question we sort of started. The only thing I want you to notice, so a spherical balloon is deflating, okay? So I want you to pay attention to this and what it means. That's really the main reason I picked that. So everything else is a repeat of the very first question we did. So the volume is 4/3 pi r cubed. dV dt is -8, and that's what I want you to pay attention to, because it's losing air, okay, or deflating, minus it. Other than that, it's the repeat of the same question, just the numbers are different. R is 20 centimeters, take it from there. Now we know the differentiation, it's very simple. We've done that already, okay? So Everybody remembers that if you go back to the very first example, 4/3 pi times 3r squared dr dt. So 4/3 pi times 3r squared dr dt. That's what we did. And that gives us 4 pi r squared dr dt. Replace it accordingly, you have the answer. It's really not a big deal, okay? And I wouldn't worry about that. You are finishing the job and you get -1/200 pi. Again, class, I'm going over this pretty fast because you have seen this, and again, you can do the approximation. As far as the simplification is concerned, I can say 4 goes away and 8 becomes 2. Okay. 2 changes to 1. 400 changes to 200. And this is your precise answer. Okay. And -1/200 pi centimeters per minute. Then you can write the approximation also in case. So this is the same question. We have made a slight change. So I hope everybody is comfortable with that. Okay. All right. Here's the next question. If the minute hand of a clock has a length of r, whatever the units, in this case centimeters, find the rate at which it sweeps out area as a function of theta. Okay. Well, first let's do the drawing so we understand what's happening here. So this is a circle. This is the central angle theta. This is the radius r. Okay. So first, I want you to know that we have the arc length s equals r theta, and then we have the area that we are interested in. Okay. So s equals r theta, area is 1/2 r squared theta. I hope you remember this from trigonometry. Okay. And one way to remind you of how we got that is that if you recall, the area of a circle is pi r squared, okay? Or you can say 1/2, okay, r squared times 2 pi, and that's basically what is going to be 2 pi is replaced by theta. That's the concept. So this is how we justified it in trigonometry. I'm just refreshing your memory. Okay. So A is 1/2 r squared theta. We want to find d8 dt. And remember, what is r? R is not changing. The radius of any circle, okay, a circle like this, okay, you're looking at the clock. So its radius is fixed. It's just a number. We may not know what it is, but it is just fixed, okay? Length r, okay? Length r is a fixed length. So you want to find the ADT, okay, class? So to find the ADT is pretty simple. The ADT is 1/2 r squared, this is the number, times theta becomes d theta dt. So the ADT is 1/2 r squared d theta dt, d theta dt. And believe it or not, that's it, and you're done. You want to find the ADT for any r. And of course, if r is given, you just replace it, you come up with the answer. By the way, maybe the ADT is given, maybe r is given, you can find the missing one. For now, this is a general format. So, for example, if we do it over the course of 1 hour, that covers 360 degrees or 2 pi, okay? If you plug in, you get pi r squared centimeter squared per hour. So take a look at what happens. It's interesting. Over the course of 1 hour, we cover a complete revolution. A complete revolution is 360 degrees or 2 pi radians. And so we are going to replace that, okay? And we come up with the answer, which is pi r squared centimeter squared per hour. All right, we want to look at the next example. Could somebody read this question for us, please? Anyone?
The length of a rectangle is increasing at a rate of 8 centimeters per second, and its width is increasing at a rate of 3 centimeters per second. When the length is 20 centimeters and the width is 10, how fast is the area of the rectangle increasing?
Thank you so much, Nicole. So pretty straightforward. We want to see what's going on. The first thing first, it's asking how fast the area is increasing. That means we should be able to relate the area to the width and the length. And as you all know, the area is length times the width, or width times the length anyways. So the length of a rectangle is increasing at the rate of 8 centimeters per second. That means the LDT, okay? And the width, dW dt, is 3 centimeters per second. The length is 20 centimeters, and the width is 10 centimeters. So everything is given. You know the area. The LDT is given. That's the LDT. dW dt is given. Okay, the width is increasing. The length and the width, find the ADT. It's really pretty straightforward. So what do? We're going to differentiate this. So we want the ADT. And to differentiate this, it's extremely important to understand we are using the product of L and W. Therefore, we are using the product rule class. We are using the product rule. Therefore, the derivative of L is the LDT times W. The derivative of W, okay, is dW dt times L. In any order you want to put that. In any order that you want to put that, it's fine, everybody. Okay, so L dW dt plus W dL dt, put it in any order and that's fine. Okay, and everything is given. Look at your given. You wrote everything here. You don't have to look for anything. Just plug everything in and find the missing one. So we are putting everything on the right side, and we get 140 centimeters per squared per second. It is important to see that, again, the ADT, the units of the numerator over the units of the denominator, okay? The units of area over the units of time. Also, if you want to go this route, 20, okay? 20 what? Centimeters. Number 3 what? 3 centimeters per second. Same unit here if you work it out. So that is important for everybody to understand, okay? And it's, we really don't want to, mess it up. So I hope everybody is okay with that, okay, class? So let's take it from there. All right, could somebody be kind enough to read this question, please? A street light is mounted at the top of a 15-foot tall pole. A man 6 feet tall walks away from the pole with a speed of 5 feet per second along a straight path. How fast is the tip of his shadow moving when he is 40 feet from the pole? When you do problems that are ultimately applications and word problems, you really have to set up. So take a look at the setup and see what's happening, okay? All right, so here's the pole, okay? And somewhere is the man moving away. I hope you see that. The man has a speed, okay? So this is 15 feet tall, okay? The man is 6 feet tall and is moving at a speed, okay, if we call the distance x, at a speed of dx dt, or 5 feet per second. okay? Now the tip of the shadow is moving at a different speed, and we don't know. Remember, I mean, just you can even imagine that you're moving and what happens to the tip of your shadow. And so with that being the case, if the distance that it makes from the pole when we move, the man has a distance of x, the tip of the man's shadow has a different distance. What is it? We don't know. Well, let's give it the variable y. Okay, so let's see what we want. Here's the given, everybody. And by the way, this is also a drawing that looks a lot better. Okay, so 15 feet. We are getting away from the pole. We have a certain speed. Okay, and we want to see what happens. So if you look at that, the x dt is 5 feet. Okay, everybody, per second. The y dt is of interest to us. At a precise moment that x is 40 and man covers, okay, x feet, remember that, while the shadow covers y feet. All right. So let's see what happens here. I hope you see that we have what's called similar figures. Okay, so what are similar figures? Okay, similar figures are figures that their corresponding angles are identical and the corresponding sides are in proportion. So I hope you see that if you look at this triangle, okay, versus the large one, okay, they are similar figures. So if I'm looking at finding the ratio, here's one easy way. I hope you see that this is one side, which is 6. This is another side, which is 15. So 6 to 15 would be this distance over the total distance, or would be this distance over the total distance, okay? So this distance is what? This distance is x, and the whole distance is y. So what is this distance, class? Let me use a different color. Let me see what color I can use to. What is this distance? By the way, this y, class, we really mean this, okay? This is y, okay? If you choose that one to be y, okay, then we have a y over x plus y, okay? So it really depends how you write it. So I think it's easier if we choose the whole thing to be y, therefore this little part is y minus x. So the ratio of 6 to 15 is the same as y minus x over y. So I hope you see what I'm doing here. Similar figures. The ratio of y minus x to y, my apologies, is the same as the 6 to 15. And of course, we don't need the hypotenuse because we don't have it and we don't need it anyway. So I hope everybody can see what happened. So I'm going to quickly recap. I'm looking at the small triangle versus the large one. The small triangle has the sides y minus x, okay, y minus x and 6, y minus x and 6. The big one, here's the big one. The big one, corresponding to 6 has a side 15. Corresponding to the little side y minus x has this whole thing. What is this whole thing? Y. Okay, everybody? This whole thing is y. So I hope everybody understands what's happening and everybody's okay with that. So having said that, now it becomes a piece of cake, everybody. Cross product, okay, and simplify. So 15 times y minus x, y times 6. So when we go through the process, and I'm assuming everybody can see that this is 15y minus 15x equals 6y. So you are going to subtract 6y and you're going to move the negative 15x, and that's what we get. 9y equals 15x, y equals 5/3 x. Now, what is dy dt is 5/3 dx dt. Okay. So whatever dx dt is multiplied by 5/3, it's a tad more. So it's 25/3 feet per second. I hope everybody is comfortable with that. Okay, class? I hope everybody is comfortable with that. So having said that, we are ready to move on. We want to find dy dt for this equation. And I hope you realize we just have to plug it. There's really nothing else we have to do. Let's differentiate. Can anybody give me the differentiation of this? How would you differentiate this? Because plugging in, I wouldn't worry about, becomes basic math. I'm interested in one step. Differentiate. How would you differentiate this? Remember, when they say dy dt, that means every variable is a dependent variable with the exception of what? T. So what do you get? Anyone? Okay. Now 4 sits in front. You write the same thing to the power of 3, and then the derivative of the parentheses is 5 dx dt plus dy dt. Minus x becomes dx dt, and this is a number, becomes 0. So quick recap. 4 sits in front. You write the same parentheses to the power of 1 less. That means 4 minus 1, which is 3. Differentiate the inside, and then minus dx dt equals 0. I wouldn't worry about the rest, and I'm not going to waste my time. You just plug in. And I'm going to assume everybody can finish the job. So I really want to move on, because the purpose of this question is this. Can we do this? I don't worry about the rest, just plug in. So all of this is basic math. Let's move on to the next question. Plug in, come up with the answer. Plug in, come up with the answer. At noon, ship A is 150 kilometers west of ship B. Ship A is sailing east at 35 kilometers per hour, and ship B is sailing north at 25 kilometers per hour. How fast is the distance between the two changing at 4 p.m.? So let's find out how the setting is. So the very first thing, there's a distance of, let me just use my, okay. There's a distance of 150 kilometers between the two, okay? So that's the first thing. I hope everybody can see the setup. So A is going this way. At 35 kilometers per hour. And B is going up north at 25 kilometers per hour. Okay. X is traveled by ship A. So A goes this way by X amount, and B goes that way by Y amount. Is everybody with me? A goes this way by X, and Y goes up this way by Y. So A has moved X amount at some point, okay? So that's how we arrive at this setup. X, this distance is 150 minus X, this distance is Y, and we want to see what's happening with Z. So I hope you see the setup. If you put this in a slideshow, it gives you precisely as to what's going on. So dx dt, dy dt, t, everything is given. What is missing? dz dt. And I hope you realize with this setting and with this given, practically we are done. All we have to do, remember to use Pythagorean theorem, okay? Pythagorean theorem, which is what? A squared plus B squared equals C squared. So what is A? One leg is 150 minus X squared. The other one is Y squared. And the hypotenuse is Z squared. Almost done. Differentiate. How do you differentiate that? 2 sits in front. 2 times 150 minus X times the derivative of the inside is minus dx dt plus 2y dy dt equals 2z dz dt. Okay. Now, when did we say at 4 p.m.? Okay. At noon. At noon. At 4 p.m. that means 4 hours later. So class, 4 hours later we can calculate x and therefore 150 minus x, and we can calculate y. I'm saying you can plug in here and find everything, okay? You can calculate x, plug it in here. Dx dt is 35, we have it, 2y, okay? Dy dt we can calculate, we have the value of y and z and everything else, plug in, because it's 4 hours later. So what is x? 4 times 35. What is y? 4 times 25. Okay. So x is 4 times 35. Y is 4 times 25. So over here, by the way, I can, before even I move on, I can do this. I can say I'm going to factor out the common factor of 2. That makes the tad easy. And so we have 150 minus x. We said x is 140 quantity squared. Okay, plus 100 squared equals z squared. We find the z. Okay, everybody. Z is square root of 10, 100. And now just plug in into this formula. Plug in into this formula. I would have dropped the 2, but doesn't matter. So if we keep the 2 and then drop it. So 2 times 150 minus 140 times negative 35 plus 2 times 1. So just plug in everything. But in order for you to plug in everything, the only missing would be x. We find it from 4 p.m., y from 4 p.m., and z from this formula. Okay. And I'm going to assume you can do the math. There is a little bit of a math involved. Okay, class. There's a little bit of a math involved. I hope you are okay with that. Okay. You are okay with that, I hope. All right. So let's look at a different example. A lot of these examples, you really have to spend a lot more time later on to really get comfortable with the concept. All right. A spotlight on the ground shines on a wall 12 meters away. If a man 2 meters tall walks from the spotlight toward the building at a speed of 1.6 meters per second, how fast is the length of his shadow on the building decreasing when he's 4 meters from the building? Okay. So again, let's look at the concept and the setup. Okay. So there is a spotlight. Okay. And there is a wall, and this distance is 12 meters, class. So we have a spotlight, we have the wall, and their distance is 12 meters. Okay. So if a man 2 meters tall walks from the spotlight, so from the spotlight, the man is going to go this way. Okay, remember, when you're here, the spotlight, it looks like this. Remember, as we get away, we get shorter in essence from the spotlight, and this, okay, this is the, shadow, and it comes down. I want you to see that, okay? And so as the man moves and covers X amount going this way, this by the speed of 1.6 meters per second, okay, the shadow that, okay, first he's here, the shadow is here, okay, then it's coming down. So he's moving this way, creating dx dt. The shadow is coming down, creating dy dt, okay? So this is x, this is y. I hope everybody understands what we are trying to do here. So take a look. So here's the spotlight, here's the man, and here's the wall, and it's going like this, okay? So when we move, okay, the man moves how much? By X amount, okay? Then this starts coming down. So it looks like this. So the man has moved X amount. So now it has a distance of 12 minus X from the building or the wall, okay? And then dx dt is given to be 1.6 meters. Don't forget that the man is what? 2 meters tall, and this distance is 12 meters, original distance. So let's write the given. When man covers x feet, its speed is dx dt. Dx dt is 1.6 meters per second, okay? dy dt is missing when x is 12 minus 4 or 8 meters. You can think of it as how we arrive at x, okay? Remember, okay? X, and this distance is 12 minus x. I hope it's clear to everybody. Now, again, you're looking at a similar figure. Look at this one. This is the small one, class. There's a different color. What color? Oh, maybe this one. Okay, this is the small one. Okay, that's the small triangular shape. And look at this one. This is the large one. Okay, so how do we write that? Again, you can do the same thing. Okay, you can pick 2 from the small one, y from the large one. You can pick x from the small one, 12 from the large one, or different ways of writing it. On purpose, I've done it slightly different here. Okay, remember, you want to relate x and y. That's why they must be there. One way you can choose y from the large, 12 from the large. So 2 corresponding to y from the small, and x corresponding from the small. That's another way of doing that. Okay, class, is this the only way? No, but this is one way to do that. Okay, so as long as we have this, we are practically done. We can solve for y because we are interested in dy dt. So when we solve for y, we get 24 over x, or 24x to the power of -1. Okay, this is a very simple differentiation. Okay, now dy dt is 24 times -1, okay, x to the power of -2 times dx dt. Okay, so maybe I write that. This part, okay, should give you 24 times -1, x to the power of -2 dx dt, and you rewrite it, okay? And after that, you rewrite it in this fashion. So now you have everything plug in, remember, okay? We said x is 8 feet, so you plug it in. And I'm hoping everybody can simplify. We don't have any problem with that. So what does it mean? The length of his shadow is decreasing because it's negative at a rate of 0.6 meters per second. 0.6 meters per second. Okay. Again, we used similar figures. Pretty straightforward. A bow A boat is pulled into a dock by a rope attached to a bow of the boat and passing through a pulley. We can see the picture. That is 1 meter higher than the bow of the boat. If the rope is pulled in at a rate of 1 meters per second, how fast is the boat approaching the dock when it is 8 meters from it? So very simple. Let's first and foremost do this drawing. So take a look at this drawing, class. According to this drawing, okay, this is fixed at 1, okay, all right, and we are moving this way, okay, the rope is moving this way, and the boat is moving this way, obviously, right? So what is given? If we are pulling the rope this way, dy dt, and what's happening? Okay, please understand, this is why when you're pulling the rope, what are you doing? You're making the rope smaller and smaller. Okay, so it's negative 1 meters per second, and the dx dt is missing. That's what we are interested in when it's 8 meters away from the dock. So take a look. dy dt is negative 1 meters per second. Dx dt is missing when x equals 8. And why is it negative 1? Because rope is getting smaller and smaller, class. I can't emphasize this enough. All right. So Pythagorean theorem, x squared plus 1 squared is y squared. So x squared plus 1 squared equals y squared. Okay. All right. Now differentiate both sides. 2y dy dt equals 2x dx dt. 1 gives you 0. So just plug in. You have a choice. You can solve for dx dt, or you can just plug in. Either way makes no difference, class. If you solve for it, you get dx dt is y over x times dy dt. Okay, of course, we need to know when x is 8, everybody. When x is 8, what is y? So 8 squared, 64, and 165, square root of that. Okay, so calculate that. Y is square root of 65, and now you have everything plug in. So dx dt is y over x, or square root of 65 over 8 times negative 1, and you can approximate it now, and you get negative 1.01 meters per second. Because this is only 1 meter long, it's fairly small, they're almost moving at the same speed. Okay, class, they're moving almost at the same speed. All right. A cylindrical tank with radius 10 meters is being filled with water at a rate of 7 cubic meters per minute. How fast is the height of the water increasing? Now, of course, you should draw a diagram, and what matters is you are relating the radius, okay, and the volume. So what is the volume of a cylindrical shape? I hope everybody remembers that. So first and foremost, this is the case, and the volume is pi r squared h, okay? The radius is 10, and the volume is fixed, everybody. The radius is fixed at 10 meters, and the volume is pi r squared h. So dv dt, okay, it's being filled. dv dt is 7 cubic meters per minute. R is fixed at 10, okay, and dh dt is missing. Because R is not changing, you have to replace this, class, okay? You have to replace this, okay? So R is fixed. I'm writing the formula in general. This R is that the same one. So you plug it in, okay? Please understand R is fixed. You can differentiate or you can replace it and differentiate it. Either way is fine. R is not going anywhere. It is the H that gives you dH dt. So two choices. Replace the R, make it pi times 10 squared or 100 pi times H, or just keep it as a fixed R. The reason I want to keep it as fixed R because the question may not give you 10 meters, may give you just fixed R. R is fixed. You should know that R is fixed, by the way. Okay, R is fixed because the radius is not changing. So having said that, now you just plug in dV dt is 7 pi, R is fixed at 10, dH dt, and the units for the height per the units of uh, time. The units work out just the way they do work in the case of dealing with numbers. What we do to numbers, we do to units.